Now we go one layer up from the physical layer to the MAC layer. This figure shows you the architecture of the MAC layer plus the underlying physical layer. So here we have the physical layer. So based on these different physical layers, I explained some of them, you will find the so-called distributed coordination function, DCF. That's basically the heart of the access mechanism. I will explain exactly this core component in some more detail. And what is quite important, it is a distributed system. So in the classical operation mode, you do not have a central administrator like the access point. We will see there are new operation modes where the access point plays a special role. But in the classical wireless LAN, all stations and the access point are the same when it comes to the medium access. So the DCF, the distributed coordination function, that is used for different services that are on top of it. So the so-called hybrid coordination functions, the mesh coordination functions, and the now obsolete PCF point coordination function. So this PCF was in the early standards, but not really used, never used. So, and maybe it will drop out of the standard in the future. You see that there are some services that offer quality of service with different parameters, different priorities, some services for mesh. And I will explain in more detail, as I said, the DCF, the coordination function distributed, and give some insight to the EDCA. I will come back to this. So that is a mechanism that supports certain quality of service parameters to differentiate between different data streams. So prioritized coarse services. As you see again, that's typical for the standard, many options, different services, but not all of them are really used. Okay, so what do they do, those different functions? As I said, the core component is the distributed coordination function, DCF. That's a fundamental access method. That's mandatory. So all devices have to know how to do this. So this technology is also known as CSMA CA, so carrier sense multiple access with collision avoidance. You know that CD, collision detection, doesn't work, but at least collision avoidance. We will learn that there's a random backoff mechanism. The DCF contains certain fairness, and you can use RTS CDS for the hidden exposed terminal problem. The PCF, point coordination function, was never really used, and maybe you will not find it in the new versions of the standard. So that was a kind of an explicit reservation scheme controlled by the access point. Then what is new since several years is so-called hybrid coordination function, HCF, and that is a function that supports quality of service using different components of kind of access point controlled and decentralized scheme. And what is important here is the so-called contention-based channel access. You see that, there can still be some contention, that means collision. And this is called the enhanced distributed channel access, EDCA. And there is another method called controlled channel access where you really have a control. So I will explain some more detail this enhanced distributed channel access that supports different priorities. And the classical 4 priority classes, the access classes, are background traffic, best effort traffic, video, and voice. Voice with the highest priority, background with the lowest priority. And these are the designation the Wi-Fi Alliance gave them, and this is called wireless multimedia, WMM, wireless multimedia. So if you read this term, wireless multimedia, think of the 4 traffic classes: background, best effort, video, and voice. And we will learn that these traffic classes are implemented by using different priorities when it comes to a contention-based channel access. And for mesh networks, there's the so-called mesh coordination function only for the mesh networks. Again, a contention-based and a contention-free. So contention-free or controlled access, that means that you have a central controller that actually can guarantee that there's no collision, well, at least not inside your own wireless LAN. You can always have neighbors. And contention-based, that means that different data streams, the packets, may compete for access, and maybe you have collisions. Okay, so how to implement different priorities, how to implement different traffic classes. A very important concept in the medium access control in 8.2.11 is the so-called interframe space. So, the idea is to implement different priorities for data streams by using different interframe spaces. So, if you have to wait for a shorter time, this means you have a higher priority. If you have to wait for a longer time, this means you have a lower priority. Why? Well, the idea is as follows. If nothing is going on for a certain time on the medium, then you can directly access the medium. And then the medium is busy. And this is why all the devices check the channel. So you have this clear channel assessment signal. And this signal tells you if the medium is busy or not. If the medium is busy, all the stations have to wait. No one is allowed to send. Not the access point, none of the stations. Because if you start sending now, you will create interference and destroy a packet. Okay, now sending ends, and all the devices will hear at a certain point in time the channel is clear again. Now who is allowed to send? Well, all the stations have to wait for a certain time. Here in boldface is the short interframe space and the DCF interframe space because they are quite important for the classical DCF scheme. I will explain them. And additionally, the AIFS, the arbitration interframe space, important for quality of service. So what happens now? Now the medium is not busy anymore, and now it's not allowed to start sending immediately, but it depends on your waiting time. So if you have high priority data, for example, you have to wait only for SIFS, the short interframe space. This short interframe space is used for acknowledgements, clear to send, some polling response, etc. So acknowledgements, as we will learn, quite important, will be sent after short interframe space. The classical access happens after a DIFS, the DCF IFS. That's for the normal asynchronous data service. What does it mean? As soon as there's a packet waiting, with a waiting time only short interframe space, so for example an acknowledgement packet, this packet will have a higher priority because it has a shorter waiting time. And as soon as you start sending this packet, the medium is busy again, and then all the other stations have to wait. That's the idea. So that means if you have a higher priority, the system will give you a shorter waiting time, and then you're allowed to access the medium before the other stations can access the medium, because maybe they have to wait for DIFS. So that's the idea of priorities. Priorities are reflected in waiting times. Okay, I will also explain when contentions will happen, because maybe several stations have the same waiting time. So if you have two stations waiting here for the DCF interframe spacing, then they may want to use the medium exactly at the same time after waiting for this time. This creates collisions. We don't like collisions because collisions destroy data. So this is why we have a special, solution mechanism that tries to resolve the problem. But we have contention and there may be collisions. What else can we learn? We have the A arbitration IFS, and this is how we implement priorities. And with the help of priorities, quality of service. That means if you have a lower priority, background traffic for example, you have to wait for a longer AIFS time. If you have a higher priority, then you wait for shorter AIFS time. And this can more or less statistically guarantee a certain higher priority. So if you have a shorter waiting time, you will always win over the stations with a longer waiting time. That means data streams with lower priority. But still, there could be two, for example, voice data streams from two stations using the same IFS. So, if you belong to the same class, access class, for example, voice traffic, you use the same waiting time, and there may be a contention because you try to access the medium at the same time, and we have to resolve this problem. So, CIFS, diffs, AIFS, these are different waiting times reflecting different priorities. Then there are some more specialized beamforming IFSs, extended, etc. Not that important to explain the basic mechanisms. So you should understand that priorities are reflected in waiting times. The longer you have to wait, the lower your priority is. But there may still be some contention at the same waiting time because the sending of the stations is normally not coordinated by the access point. So the access point does not know when a station wants to send. The classical DCFS is a completely distributed mechanism. So you don't know when the stations start. And it's quite important that after the medium is busy, that you somehow spread the access to the medium, because otherwise you have the collisions always after the medium was busy. And we'll learn why acknowledgements, for example, will always be the winner compared to normal data. So the interframe spacing is a very important concept when it comes to the implementation of the medium access and implementation of quality of service. So how does it work? In some more detail. So first of all, well, as you learned, if the medium was idle for a longer time, you can start sending. But now let's assume the medium was busy and some other station stops sending after some time. So if you want to start sending here, you're not allowed to. You have to check the medium, so carrier sensing, based on the clear channel assessment. So if the channel is clear, then you have to wait at least for your assigned interframe space. If you're an acknowledgement packet, you wait for the short interframe space. If you are a normal packet, you have to wait for the DCF interframe space, DIFS. So now let's assume you have to wait for a DIFS. So the problem is that maybe several stations wait for the DIFS, and if you now access the medium right here, it's pretty clear that you will have a collision because typically many stations wait for the access. So this is why you have to wait for an additional random back-off time to avoid collisions. So you cannot guarantee a collision-free access. No way. But you can at least avoid a collision by spreading the medium access in time. So the point is you pick a random number and you have to wait for random number times a slot time, for example 20 microsecond. So if you pick for 5, for example, then you have to wait for 5 times 20 microseconds, so 100 microseconds. And after this, well, you cannot simply access the medium. No. All the time, from this very moment, you have to check the medium all the time if the medium is busy. So you have to check if someone else accesses the medium. If this is the case, you stop your back-off timer. So let's assume you pick a random number 5 times 20 microseconds. That means you have to wait for 100 microseconds. Now you count down, and after, let's say, 40 microseconds, someone else accesses the medium. That means your timer stops at remaining waiting time of 60 microseconds. So someone else has a lower random value. That means another station is allowed to access the medium before you can access it. That means you have to wait. You cannot then simply access the medium after your time. No, you have to wait. Then the other station accesses the medium, sends, and now that's the point where fairness sets in. After the other station sending, you start again, waiting for diffs, but then you do not have to pick a new random value, but you can use your old one. And this makes sure that over time, even if you picked a high random number, it will be your turn sooner or later, depending on the behavior of the other stations. Still, there can be collisions, because another random value is exactly the same, or the remaining time is the same, etc. So that is the idea. So you try to avoid the collisions by spreading the access using the random number, and you keep a certain fairness by storing the remaining back-off time. Okay, so let's bring this all together. Now let's assume we have 5 competing stations. This is all simplified. I do not show any acknowledgements, etc. So that's the basic mechanisms, just to make this a bit more clearer. So we have 5 stations. The orange arrow indicates a packet arrival at the MAC layer, so the station wants to send something. So no matter if this is an access point or one of the other stations. So in the basic mechanisms, they are all the same. So there's no central access point controlling the medium access in the DCF scheme. So this is the classical distributed coordination function. So it's distributed. Okay, so station 3 is the first one that wants to send, and there's also station 1 that wants to send, etc., etc. So we learned that the station has to check if the medium is idle for a certain time. So then station 3 checks for a certain time, and after the time is over, it simply starts sending. Okay, 1 also checks, but then suddenly, oh, the medium is not idle anymore. Okay, now station 1 has to wait until the medium is idle again. So that's here. But then also not only station 1 waits here, but also station 2 and also station 5. The stations learned the medium was not idle. That means they have to wait, all 3 stations have to wait at least for the duration of this DCF interframe space. Then, that's the next step here, they all pick a random number. And, well, this is a random number. It could be quite large. You see, for station 1, picked a larger number, station 2, a pretty small one, and station 5, something in between. So that's the initial random value they picked, and they have to wait random number times a slots. So the lowest random number was picked by station 2, and this is why after the back-off time elapsed, that's the BOE, station 2 is allowed to access the medium. Station 1 and station 5, they both detect, oh, medium is busy, too bad, we are the losers. So exactly at this point in time, they stop their timer and they have a residual backoff time, BOR, and they store the residual backoff time. All stations have to wait until sending is over. Now we are here. That means station 2 stopped sending, and now, well, station 1 again is waiting here, and then, oh, there's a new station. Station 4 is also waiting. Station 5 is waiting. Now they all have to wait for their DIFS. Station 4 has to pick a new random value, so that's a new one. Station 1 takes over the residual random time, as well as station 5. So 1 and 5 take their old stored residual backoff time as the new backoff time, and station 4 has to pick a new one. Now you count down, and now it happens that station 4 picked a random value that is equal to the residual backoff time of station 5. This may happen, okay. And then we have a collision because they both access the medium at the same time and the packets collide, interference, packets are destroyed. So DCF does not guarantee medium access, just tries to avoid the collisions. For station 1, this means, again, I lost this competition, there's again a residual backoff time. And this is then the backoff time used the next time. You see this, well, fairness component here. So although station 1 had a high random value in the beginning, it counts down, and finally, after waiting of diffs, now it's station 1's turn. And after a collision, station 4 and station 5 have to pick a new random number, a new one. Okay, that's the basic mechanism. You see, there still can be a collision. At least the system supports stations waiting for a longer time, but it depends on the random value what happens. There's some additional mechanism to even more spread these random numbers in case of collisions. I will come back to this in the next slide. You should understand this basic setting to understand the DCF. So how does the sending really works? Now let's have a look at the classical sending of a unicast packet. We learned we have to wait for a certain time, for example, then contention not shown here, maybe there's nothing going on in the medium, then we send our data, and now the receiver of the data will send back an acknowledgement. That's important because you do not know if your data has really reached the receiver. So this is why we always have an acknowledgement mechanism, and the acknowledgement is sent back after a short interframe space. Why after a short interframe space? Well, a short interframe space is shorter than the DCF interframe space. That means, although there might be some other stations waiting, they have to wait for the DCF interframe space. But as the short interframe space is shorter, the acknowledgement will always go through. And there should be no collision because it's a unicast packet, so there's only one receiver that sends the acknowledgement. That means that uses the short interframe space. So that's the basic idea. And then you will receive the acknowledgement and everything is fine. So that's the idea of the immediate acknowledgement. What happens in case of transmission errors? Well, transmission errors typically happens if you have interference. And one reason for interference is an increasing number of competing stations. So, and one way of helping out in this situation is an increasing contention window. So, if you pick your initial random waiting time, you start with a minimum contention window of 7. That's the initial attempt. So you pick your random value out of this interval, up to 7. If there was a error in the transmission, so you have to retransmit, you double the size of the window. So you pick between 0 and 15. And then again you double it for the second retransmission. Again you double it for the third retransmission. You double it again, and then there's an upper limit. So you see how the window increases the more often you have to retransmit data. What is the effect? Well, you spread your random numbers because you pick now, if you have experienced several retransmission for a certain packet, well, you really spread the random values. So all the stations that experience a retransmission have to double their window up to a certain limit. So that means, well, it might take a bit longer before you then retransmit finally the packet, but you avoid collisions. So that it's quite clearly a mechanism that helps avoiding collisions, but it is also a bit unfair. Why? Think of a new arriving station. That means a station that wants to send a packet for the first time. Then this station competes with other stations that already tried several retransmissions. So for these older stations that already wait for some time and they experience retransmission, so they had to pick a random number out of a large window, well, they have a problem compared to this new station. The new station picks this small window, and the stations with a lot of retransmission for a certain packet now have to pick a large window. Because we learned for retransmissions after collision, you have to pick a new random value, but now also from a larger window. If you transmit the first time, you start with a small window. So, new arriving packets will win statistically over those waiting for retransmission for a longer time. So that's one of the problems of this scheme. Okay, so now that was the classical unicast transmission. Now what happens in case of hidden terminals? So we learned, we used the marker, this RTS, CTS, and this gives you an example how wireless LANs, .11 LANs, can use RTS, CTS. That's an optional mechanism. So as we learned, the sender, before sending the data, you send an RTS. So here RTS, after waiting for the DCF in the frame space, you send an RTS, the receiver will respond with a CTS, that's what we already learned. But the CTS can be sent directly after waiting for a short interframe space, so that no one else can squeeze in between somehow. That's the idea. So this acknowledgement via CTS sent after SIFS, if the receiver is ready to receive. And now you can more or less immediately, after again short interframe space, send your data. After, as we learned, short interframe space, you will get the acknowledgement. So you see, as soon as you get your CTS, you can immediately send data, get the acknowledgement. No one else can interfere now. That's the idea. So this is how the .11 implements RTS, CTS. Additionally, the other stations store a so-called network allocation vector, NAV. What does it mean? As soon, we learned this from the RTS, CTS scheme, as soon as you hear that there's a communication going on, you can internally store that the medium is blocked for a certain time until the communication is over. We learn this by looking at the RTS and CTS packets. This could be different stations, remember, hidden exposed terminals. But then at least those stations learned that, okay, we have to remain silent for a certain amount of time because the RTS contains the duration of this whole procedure, as well as the CTS. So that means the stations learn to be silent. And this reduces potential interference. So you store this network allocation vector. Okay, you see here hidden exposed terminals solved by using RTS, CTS as we learned from Marker in the early chapters. .11 knows also fragmentation. So fragmentation, that means you can send several fragments of a larger packet. And to make this more efficient, the waiting times here in between are only short in the frame space. So it's basically a ping pong of fragment and acknowledgement. And you also see the updates of the network allocation vectors, so to reduce the interference by other stations so that the other stations remain silent during this exchange of data. So fragmentation is another mechanism in .11. Okay, so that is the basic idea of exchanging data in a wireless LAN. And for sure, there's also a frame format. Again, the single fields are not that important, just the basic components. So all the frames, they contain at least the first three and the last field. So that means a frame control, a duration or identifier, and at least one address field and a checksum. There are different types of frames, control frames, management, and the data frames to transmit your data. Sequence numbers, that's important for duplicated X, so classical sequencing. Addresses are a bit different from what you may know from classical Ethernet, because here we have up to 4 different addresses. We will learn in the next slide why we have 4 addresses, but we have to distinguish between logical senders and receivers and physical sender and receivers. And depending on how you use the packet and where you use it, the role of the address fields are a bit different. So you have real transmitters, physical transmitters, and the logical sender. That's a difference depending on how your network topology is. I will come back to this later. And then we have the classical checksumming and sending times, frame control, etc., etc. And in the frame control, again, you have some more bits indicating if this is this frame is used for, has more data or not, and what type of packet this is. There are many different control packets, and also where this packet flows, if it's a packet directed towards a distribution system, coming from a distribution system. So you see, it's a bit more complex compared to a classical Ethernet frame, for example. And depending on the packet type, you need more or less of these fields. So quite interesting is this addressing. Why logical and physical and whatever addresses? Well, think of a system that, let's say, classical infrastructure. Classical infrastructure, you have your infrastructure, you have your access point, and you have your station somewhere. So station and access point. Then, depending on the direction, you set the bits in the packet. So these are for these two, that's for infrastructure, that's infrastructure network. So then, if you have a packet that goes from access point, then you set the from DS bit but not the to DS bit. And then the address fields have a certain meaning. The receiver address, so the physical receiver, is also the logical destination address. The logical address is the MAC address. The logical MAC address as you use from normal local area networks. So this is our destination address, but also the physical receiver address. Why to distinguish here? Well, think of the other direction. If you send from a station to the infrastructure, then you set to DS to 1 and from DS to 0. That means now that the destination address is somewhere in your local area network. This can be any computer in your local area network. That's the MAC address. If you remember from the fixed networks, MAC addresses, they address here the sender and the receiver of a data packet. But now this suddenly can be different from the physical receiver of the data. If it goes to the infrastructure, then our receiver address, the technical receiver, is the access point. That's our receiver. This is now our SSID, but that's the technical receiver. Why is this physical receiver important? Because that's exactly the component that sends back the acknowledgement. The logical receiver in our local area network will not send back the acknowledgement. It's the physical receiver. Because in our local area network, we don't know anything about acknowledgements. Usually you have unacknowledged packet transfer in our local area networks. So if you use a normal Ethernet LAN, there are no acknowledgements at all. You just send your data from a source address to a destination address. And as we do not have this acknowledgement mechanism, we do not have to distinguish between the logical receiver, that's in our case here the destination address, here, that's the destination, the logical destination, and the physical receiver. The physical receiver is now our access point, if we look at this. So you see, depending on the setting, if you have infrastructure or if you have a mesh network, etc., you have completely different, meanings of the addresses. Especially in the mesh network, you have a logical, that's the fourth row here, you have a logical destination and a logical source. That's somewhere. And then you have many different transmitters and receivers inside the mesh networks. These are the physical transmitters, the physical receivers, and they exchange the acknowledgements. That's important if you work with acknowledgements. So always the acknowledgements, they go back to the physical sender of a packet, from the physical receiver to a physical sender. So now you see how you can use the different addresses for different purposes. So that's quite interesting when it comes to this addressing. So we distinguish between logical addresses and these, addresses we use for the physical reception and transmission of our packets. So this is why we can have up to 4 addresses. Usually there's 3 addresses if you have the infrastructure network. And then if you send something to the infrastructure, the receiver is the access point, indicated by the SSID, and the transmitter is you, but the logical receiver is somewhere else in your local area network. Maybe your router, something like this. So it depends. And also the other way around, you are the logical receiver, you're also the physical receiver, but the physical sender is your access point. And the logical sender might be some other computer in your local area network. Okay, finally some special frames just to show you they are short. Acknowledgements, very short. RTS, CTS, also very short. And this answers the question when it comes to MACA, why can you use RTS, CTS? Yes, because they are pretty short. There can be collisions using RTS. Yes, RTS packets can collide, but not the CTS, not the acknowledgements. That's the big difference. Okay, finally some questions to the MAC layer. Why is it difficult to guarantee quality of service? You heard a bit about quality of service. Why is it difficult to guarantee something? How do we prioritize different packets? How is this mechanism really operating, prioritization? We looked at the basic access method. What happens under no load, light load, heavy load, advantage, disadvantages? How is at least some fairness implemented? And why is the contention window mechanism not really that fair? What is the idea behind the network allocation vector, NAV? And how does .11 solve the problem with hidden exposed terminals or stations in the terminology of .11?